Hello friends, so today we are going to solve some questions, and the questions are from the year 1998, and the total questions are 1998 are 2, 1999 we are having 4 questions, and from the year 2000 we are having 3 questions. So in totality there are 9 questions. Okay. So first question, it was asked in the year 1999, and it states that in the circuit shown in the figure, the battery is an ideal one with EMF V. The capacitor is initially uncharged. The switch S is closed at time t is equal to 0. Find the charge on the capacitor at time t. Part B. Find the current in AB at a time t. What is the limiting value as t tends to infinity? So the basic circuit is given to us, and there is switch S. Initially it is open, and the EMF is given as V, and the resistances in the circuit are all same, having the same value, that is our R. And the capacitor C, in the first part we are supposed to find out what will be the charge on the capacitor at a certain time t when the switch is closed. Okay. And let us assume that when the switch S is closed, the current that is flowing, let us call this as current as I1, and the total current here, if that is our I, then we can say this is equal to I minus I1. And we are given AB, and let us call this as let us call this as C, D, E, and F. And so at time t is equal to 0, switch S is closed. So it is given to us. So you can say at t is equal to 0, switch S is closed. And as soon as switch S is closed, the capacitor is going to charge, and it is said that in the part A it is given that find the charge Q at a time t. It means at time t the charge on the capacitor should be equal to our Q. That's a basic premise from here. And we need to find out because we can write that our current I1 will be equal to dq by dt, okay, because I1 current will be flowing through the capacitor, okay, and this will be positive as the current is going to, as the charge is going to increase. Okay, so you can say it is positive since charge increases with time. Increases with time t, and if it are decreasing, then we can put easily the negative sign. So let us use a KVL, and in the loop that is our CABFC. So we can use our KVL, and KVL in the loop is our CA, and that is our BFC. So we can just draw this loop. This is a switch S which is closed right now, and resistance, we have a EMF, and there is another resistance here. So current that is flowing here, it is of I. This is EMF, resistance R. Current flowing through here is our I minus I1, and current through this is our C, A, B, F, and this is our R, and current through here will be also equal to our I. So we can just mark the polarities with respect to the current. So this will be positive, negative, positive, negative, and let us take the loop direction in this way. So we start with the supply voltage, so that is rise in potential. Therefore we can say that our V, and then this comes as minus, we have I minus I1 times R, and this is minus R times I is equal to 0. And we can write this equation will be equal to our V is equal to, this will be coming as 2R I, and this will be minus R times I1. Let us call this equation number 1. And similarly, we can use KVL in the second loop. KVL, and the loop that is our let me draw it, and second loop is our C, D, E, F, C. Okay. So we have a switch that is somewhere here, it is closed, and a resistance. Here we have a capacitor, supply voltage, and there is a single resistance here. This is our R, this is also our R, and this is our capacitor C, and voltage V. The current through this is our C and DEFA. So this is our DEF, and the current through our R is our I1, and current through here, that is our I. So again this is plus minus, and this will also plus minus, and we take loop like this. So we can say that KVL in the loop, and that loop is our C, D, E, F, C. So we can write the equation, and that equation will be equal to our V is equal to, this comes as our R I1 plus Q upon C, and this comes as plus I times R. Let us call this as equation number 2. And from equation 2, we can just you can say remove this I1, or it is much better option to eliminate I. Yeah, that way I elimination will be much more easier. Okay, let us see how it works out, because we need to find out our I1, then we will able to find out our dq by dt. We are only interested in our I1. So let us multiply this second equation by 2, and we get this as our 2v is equal to 2I1 plus 2q by c and plus 2r multiplied by I. Okay. And let us call this equation number 3. We multiplied this equation by 2. Now we can simply subtract them, and 2r and 2r1 cancel out. So we can say that from equation 3 and 1 and 3, from equation 1 and 3, we get our 2v minus v will be equal to v is equal to, this is our 2i1, 2ri1, and this is our i1, so minus will be, this will be 3ri1 plus 2q upon c, and this ri and this ri are going to cancel. So from here we can say our I1 will be equal to, this will be equal to 3 minus, we have v minus 2q by c, and it comes as 1 upon 3r. Now we can use the equation that I1 is equal to derivative of the charge. You can say I1 is equal to dq by dt. So we substitute the I1, we get this as 1 upon 3r, and this is v minus 2q upon c. Now we can use just variable separable. So we get here our dq, and this comes as v minus 2q upon c is equal to dt divided by 3r. And we can just integrate from 0 to q and 0 to t. So we get this will be equal to, on the right side we are going to get t, and on the left side we get this as, okay, let me take the c, we can take as LCM, so this comes as vc minus 2q, let me write 1 by c, 0 to q, and this comes as dq divided by our vc minus 2q, and this we can do multiply by and divide by 2. Okay, so this we get as a, will be equal to 0 to t dt by 3r. Now it is, so this gives us that our charge q will be equal to cv divided by 2, and this comes as 1 minus e raised power minus 2t divided by 3 times RC. Okay. And this is our, I think, first part. Yeah, so this is our first part, that is the charge on the capacitor at a certain time t. And in the second part it states that find the current in AB at time t. So we have to find the current through AB, and current through AB is our I minus R1. Okay. And I1 is our dq by dt. So we can say our I1 is our dq by dt, and that will be equal to V upon 3R e raised to power minus 2t divided by 3 times RC. Okay. And we have our equation 1. So we can say from equation 1, and equation 1 is our V is equal to 2R minus R I1. Here we are going to substitute value of our I1. So it is V is equal to Ri minus 2Ri minus R times I1. And from here we can write that our current I will be equal to, this comes as V plus R times R1 and divided by 2R. We can substitute value of our R1. So this gives us V plus R, and our R1 is V upon 3 times, and this is e raised to power minus 2t upon 3 RC divided by 2R. And the current through AB is our I minus I1, and let us suppose that is our I2 for the simplicity. So we can simply write our I2 will be equal to I, and here this R and R is going to cancel out, so we get our I2. It can be written as V upon 2R plus, this comes as V upon 6R e raised to power minus 2t divided by 3RC, and our I1 is minus V upon 3R e raised to power minus 2t divided by 3RC. And we can just solve these two equations. So we can take this as common, so we get our I2 will be equal to V upon R plus, this comes as 6 V upon 6R minus V upon 3R. Okay, and this gives us 6R will be LCM, so this will be 3 minus 2, 3 minus 1. This will be not 3 minus 1, but LCM is 6R. Let me write it. LCM is 6R, so this will be coming as 1 minus 2. Okay, so this will be 1 minus 2 will be a minus, so this will become as minus, and this will be V and e raised to power minus 2t divided by 3 RC. Okay, so this is our current through AB, and we are also supposed to find out the limiting value at t tends to infinity. So we simply substitute t is equal to infinity. So at t tends to infinity, we are only going to solve this part because this contains only t, and if t tends to infinity, so this comes as e raised to power minus 2 and this will go infinity divided by 3 RC. This can be written as 1 upon e raised to power minus 2 infinity upon RC. Sorry, this will be plus now, so this comes 1 upon infinity, and this is equal to 0. Therefore, the limiting value I2 will be equal to V upon 2R minus 0, which comes as V upon 2R. Next question, and it was asked in the year 1998, and it states that a conducting sphere S1 of radius r is attached to an insulating handle. Another conducting sphere S2 of radius capital R is mounted on an insulating stand. S2 is initially uncharged. S1 is given a charge Q. Brought into contact with S2 and removed. S1 is recharged such that the charge on it is again Q, and it is again brought into contact with S2 and removed. This procedure is repeated n times. So based on this description, we have two questions. First said that find the electrostatic energy of S2 after n such contacts with S1. And part B, what is the limiting value of this energy as n tends to infinity. Okay. And here there is a contact and removal of S1 and S2 continuously, and we have to remember that when S1 and S2 are contact, the transfer of charge is going to take place until the potential at both the spheres become equal. Okay. So you can say when S1 and S2 are in contact, the transfer of charge takes place until the potential of both the spheres becomes equal. Okay, so this will be the basic premise between the entire discussion. So there are n contacts. Let us start with the first contact. You can say first contact. Initially there is no charge on S2 and the charge on S1 is given as Q. And in the first contact, let us assume that the charge from S1 will be shifted to S2, and that charge, let us suppose, is our Q1. Therefore, and this shift is going when the potential becomes equal. So you can say that V1 potential on first sphere, let us call the potential on S1, should be equal to potential on S2. Let me make it reverse, much more easier. S2, and this is our S1. And we can say that our V2 will be equal to our V1. So the potential on our, suppose the charge transferred from S1 to S2 is Q1. So after the transfer of the charge Q1, the charge that will left on S1 will be our Q minus Q1, and charge on S2, because the initial charge on S2 was 0, so charge on S2 will be equal to our Q1. And therefore we can write that our K Q minus Q1 divided by R is equal to K Q1 divided by capital R. And from here we can easily find out our Q1. Here K and K cancels out, and we get that our Q1 will be equal to capital Q, and this comes as R upon R plus small r. Now we come to the second contact. Second contact, and in second contact also V1 should be equal to V2. V1 should be equal to our V2. Okay. And so we can write that the equation will be now equal to K, and we have this as capital Q minus Q2 minus Q1 divided by small r will be equal to K Q2 divided by capital R. And in this case we have to remember that during the second contact the charge on S2 is already our Q1, and charge on S1, if the transfer, one second, let me write it other way. In this case, once again from S1, let us suppose the charge that is being transferred to S2 is our Q2 minus Q1. That is a difference between the two, because initially the charge on the S2 was our Q1. So once again we can find out from here the value of Q2, and we can say that our Q2 will be equal to capital Q, and this comes as R upon R plus R, and this comes as plus R upon, and this will be our whole square and closes. Now we come to the third contact. Third contact, and in the third contact also V1 should be equal to V2, and the charge that is being transferred from S1 to S2 is our Q3 minus Q2. So we can just replace the formula and we get this as K, and this will be our minus Q3 minus Q2 divided by small r is equal to K Q3 divided by capital R. And from here we can easily find out our Q3, and our Q3 will be equal to capital Q, and this comes as R upon R plus R plus R upon R plus R whole square plus R upon R plus R, and this comes as whole cube. So we can just, you can say, make an conclusion from all these transfer. If we see the equations, so we can derive the general equation for the transfer for the nth contact. So you can say for nth contact, our V1 should be equal to our V2. Therefore we can write that our K capital Q minus this is our Qn minus Qn minus 1 divided by small r will be equal to K Qn divided by capital R. K and K easily cancels out, and we can write that the equation for our Qn will be equal to Q, and I can write this as R plus it is going to increase by power 1, and this will be so on up till plus R upon R plus R whole raised to power n. And we can just simplify it, and we can write it as that our Q of n will be equal to QR upon small r. This comes as 1 plus R plus n and whole raised power n. And we need to find out the electrostatic energy at the nth contact for S2. You can say that energy of S2 after n contacts, and we can write this as U of n will be equal to 1 by 2 Qn square divided by C, and we get this as U of n will be equal to okay, because this is a conducting sphere. So we can write U of n is equal to over half multiplied by 1 upon 4 pi epsilon times r, and this comes as QR upon small r, and this is 1 minus r, plus, one second, yeah, my mistake, here it has minus. Minus, and this is comes r plus r whole raised to power n, and this is whole raised to power square. And next is a limiting value, so we substitute n as infinity, So we can write that limiting value we get our limit n tend to infinity u of n will be equal to limit, and this comes as n tends to infinity, and we substitute the value, we get this as 1 upon 8 pi epsilon naught r, and into this comes as qr upon r, 1 minus r upon whole raised to the power n, and this is our square and bracket closes. And if we substitute value of n as infinity, so this will be coming equal to, this is 1 upon, this will be our 8 pi epsilon naught r multiplied by q square r square upon small r square, and this r and square goes away, so we are left with 1 upon 8 pi epsilon naught and multiply by q square r upon small r square. So this is the limiting value. Okay, yeah. Next question. It was asked in the year 1999, and it states that a non-conducting disk of radius a, uniform positive surface charge density sigma, is placed on ground with its axis vertical. A particle of mass m, positive charge q, is dropped along axis of the disk from height h with zero initial velocity. The particle has q by m ratio as 4 epsilon naught g divided by sigma. So based on this description, we are having two questions. Part A, find the value of h if the particle just reaches the disk. Sketch the potential energy of particle as a function of its height and find its equilibrium position. So we are given a non-conducting disk of radius a. So we can just draw an approximate figure for that. And we have a non-conducting disk, and its radius is given as a. Radius is given as a, and we have a point P of positive charge Q. Okay, so this is our positive charge Q, and it is dropped from height h. So this is our height h. Let us call this as point P, and this is our center SO. And we have to remember that the surface charge density of this disk is also positive, and the charge that is being dropped is also positive. So for the sake of discussion, let us say that at a certain point of time, the charge which is dropped from height h, so this is our initial point P, and at any point, let us suppose the charge is at a height x, let us call this as P prime, and this is the position of charge that is being dropped, and it is a distance of x from the center O, and this is our radius a. And we consider a small disk and whose radius is our r, and that this thickness of this disk is our dr. So therefore we can say this distance will be equal to our r square plus x square and its square root. So here we have considered a small disk like this, and its thickness is our dr. So you can say that at any instant the charge plus q is at a distance x from the center O. And here we consider a small strip on the disk of thickness dr. Consider a thin strip of width dr and a radius r. Therefore, we can find out the charge on this thin strip, that is our dq. So you can say that charge on thin strip, that is our dq, will be equal to charge density multiplied by the area of the strip, that is our pi r square, and its derivative will be coming as 2 pi r multiplied by dr, okay, because it will be sigma and dA. Okay, so you can say this is sigma and this is our pi r square. Okay, so this will be giving us dq. Similarly, because of this thin strip, we can find out the potential potential at point P prime. So we can say that potential at P prime, that will be our dV, will be equal to 1 upon 4 pi epsilon naught. Charge is our dq and the distance is our r square plus x square and its square root. R square plus x square and its square root. We already know our dq, so we substitute, we get our dV is equal to 1 upon 4 pi epsilon naught. This comes as sigma, and we have this as 2 pi r times dr divided by r square plus x square and its square root. And we have to find out the value of h. Okay, so based on this we can find out the electrostatic potential at P prime. Electrostatic energy, electrostatic potential energy, one and same thing. So we can say our electrostatic potential energy at P prime, that is our U, will be equal to 1 upon 4 pi epsilon naught, and that will be our integration of 0 to a, and for the electrostatic potential energy at P prime due to entire disk, and we can write this as sigma upon 2 pi r, and this comes as dr divided by r square plus x square and its square root. And our dq multiplied by charge q. Now it's complete. So therefore we can write that our u will be equal to, we can take rest of things as common, and we left with 2 pi q sigma, and this is our 4 pi epsilon naught 0 to a, and this comes as r square plus x square minus 1 by 2 and multiply by r dr. And this integral is quite easy to solve, so we can just write the result. So we get this as u is equal to, this will be coming as sigma q divided by 2 epsilon naught, and we come this as x will be over a, so this will be a square plus r square, sorry, a square plus x square, because the derivative is our r, and whole raised to power 1 by 2 and minus of x. So this is our electrostatic potential energy at point P, and it states that the particle is released from point P. So therefore we can use the conservation of energy. It says that particle is released from point P, and that point P is at a height h from the center of the circle. So we can use conservation of energy. Conservation of energy, and this conservation of energy will be used that energy, total energy at point P should be equal to total energy at point O. So at point P it is going to have the potential energy as well as the electrostatic potential energy. So you can say the potential energy plus electrostatic potential energy is our u, but the u is to be found out at x is equal to capital H. That will be equal to the total energy at point O, potential energy at O. So you can say potential energy at O, and let me write potential energy H, plus electrostatic potential energy when x is equal to 0, plus, and yeah, that's all. So potential energy at height h, we can write this as mgh plus the electrostatic potential energy at x is equal to h. So in this equation number 1, we simply substitute x is equal to h. So we get this as sigma q upon 2 epsilon naught, and this will be over a square plus h square 1 by 2 minus h, and potential energy at point O, obviously height will be 0, so this will be coming as 0, plus potential energy, electrostatic potential energy at x is equal to 0. So once again in equation 1 we put x is equal to 0. We get this as sigma q upon 2 epsilon naught, and this comes as a square plus 0 1 by 2 and minus 0. We are already given that the ratio of our q upon m is given to us. Yeah, q upon m is given as 4 epsilon naught g upon rho. So we are given, but q upon m is given as 4 epsilon naught g upon sigma. So from here we can write our q is equal to 4 epsilon naught gm divided by sigma. So we substitute value of q and we get this as mgh plus this is your sigma upon 2 epsilon naught, and q comes as our 4 epsilon naught gm sigma, and this is our a square plus h square square root minus of h is equal to, and on the right side sorry, this will be same sigma upon 2 epsilon naught, and here comes 4 epsilon naught gm upon sigma, and this comes as a square, its square root, and it will only a will be left. So the common terms epsilon naught sigma sigma, this goes by 2, and similarly on the other side also sigma sigma, and this goes by 2. Therefore we can write that our mgh plus we are left with 2gm, and we have our a square plus h square square root minus h is equal to, this is 2gm, and multiply by our a, and here our mg cancels out, so we get this as our h plus 2, and we can just open the bracket, we get the square root of a square plus h square minus 2h is equal to 2a, and we can solve. This will be coming as minus of h, we can take that on the right side, so we will be left with only 2. This is our a square plus h square, its square root is equal to, this comes as 2a plus h. We can just square it, which gives us as 4 a square plus h square will be equal to 2a plus h, and whole square. Now it is easy to sort it out. So we get this as 4a square plus 4h square will be equal to this way of 4a square plus h square plus 4ah, and here this 4a square cancels out, and this have h square and h square, and we get this as 3h square will be equal to 4ah, and from here we can write that our h will be equal to, this comes as 4 by 3 and multiply by a. So this is our height h. Okay. Obviously if we take as h as common, so we cannot, the h cannot be obviously equal to 0, because if height is 0 then the entire questions becomes fictitious. That doesn't help. So we get h is equal to 4 by 3a. So this is our part A, and part B, it states that sketch the potential energy of the particle as a function of this and find its equilibrium position. So we already know the equation for our energy at height x, and we know its electrostatic potential energy, and for potential energy that will be our mgx. So total energy at point x will be equal to potential energy at x plus electrostatic potential energy at x, and this will be equal to mgx plus q upon 2 epsilon naught, and this comes as our a square x square square root minus of x. Once again we substitute value of q, and we get this as our mgx plus sigma upon 2 epsilon naught, and q is our 4 epsilon naught gm upon sigma, 4 sigma epsilon naught gm divided by sigma, and a square plus x square square root minus of x. Here sigma epsilon naught 4 goes by 2, so this comes as mgx plus and this will be our 2gm, and a square plus x square square root minus of x. We just multiply inside, we get this as, this will be mgx and this will be coming as minus 2 mgx, and we can take gm as common, so this comes as gm, and this will be about 2 square root of a square plus x square and minus of x. Yep. So this is our, you can say, energy at total energy at x. Total energy at x. And we know for equilibrium position, the value of the net force should be equal to 0. Or in terms of energy, we can say that our du by dx, let me write it as not du but d of total energy should be equal to 0. So we can just differentiate. Let us call this equation 2. Therefore, you can say that derivative of this total energy with respect to x will be equal to mg, and we get this as 2. This will be our a square plus x square raised to power 1 by 2. So that comes as a square plus x square 1 by 2, and this will be 2, and 2x will be giving us 2x. Sorry, x square will be 2x. This is minus of 1 equal to 0. Now it is quite easy to solve. So mg cannot be equal to 0. So we get from here that 2 and 2 cancels out. So we get this as 2x upon a square plus x square square root will be equal to 1. And we can just square it. So we get 4x square is equal to a square plus x square, which gives us that 3x square is equal to a square. Therefore, our x is equal to, this comes as a square root by 3. So this will be the position where it will be in equilibrium, that the distance from the center origin O, and we need to find out its graphical representation. And we can just plot the graph. So this is our height h, and this is our total energy, and the initial point is important because here h is equal to 0, or we can say if we substitute h is equal to 0, we get, or in this case the x will be equal to h. So we get the total energy will be equal to, this will be 2a, this comes 0 0, this will be 2a gm or 2mga. Okay. So the graph is going to start from somewhere here. Let us suppose this is our 2mga. And next we can easily find out next known point is our x is equal to a by 3, and this is our point where the energy is the minimum. Okay, so obviously it will be lower than somewhere here, and this point will be our h is equal to a root 3 by a by root 3, and the graph will be following this, something like this. Okay, and we can also find out this point by substituting x is equal to square root of 3 in equation number 2, and this gives us that the energy for this particular point will be equal to root 3, and this comes mga. So this is the approximate graph for the energy. Next question, and it states that it was asked in the year 1999, and it states that two identical metal plates are given positive charge Q1 and Q2, where Q2 is less than Q1 respectively. If they are now brought closer to form a parallel plate capacitor with capacitance C, the potential difference between them is. And here we have to remember one key thing, that whenever we discuss the parallel plate capacitor with respect to the charge, okay, in normal cases, if the charge on first plate is plus Q, then the charge on the second plate will be our, you can say, same magnitude but of opposite sign. So here it has to be minus Q. Okay, so this is the basic behind in the parallel plate capacitor. And the potential difference, if C is the capacitance, so we can say the potential difference will be equal to Q upon C. Okay, so we are going to take any one of these charge and divide by capacitance. This is going to give us a potential difference. So obviously we are having two different charges, Q1 and Q2. Q2 is less than Q1, so therefore charge redistribution is going to take place as both the plates are brought together. So you can say that when two plates are brought close, charge redistribute itself. Charge redistributes itself. And based on this, or we can charge redistribute itself due to electrostatic induction. Due to electrostatic induction. So we can say from here that the inner surface of the plates are going to have equal and opposite charge. You can say inner surface of plates will have equal and opposite charge. So therefore you can say for the first plate, inner surface the charge will be equal to Q1 minus Q2 divided by 2. And for second plate, inner surface, it will be same but with opposite polarity. So this will be minus Q1 minus Q2 divided by 2. And because of if we add these two charges, the sum of this inner plate first added with second will become equal to 0. But according to the quantization of the charge, sorry, not quantization, but conservation of charge, before the plates were brought together, the charges were Q1 and Q2. So total charge will be Q1 plus Q2. Even if they are brought together, the charges should be Q1 plus Q2. Net charge should be Q1 plus Q2. So we have to remember that thing. Therefore, we can say that the outer surface the outer surface of both plates combined will have charge, and that will be equal to Q1 plus Q2. Okay. Only under this condition we can say that the conservation of charge will be charge will be conserved. Now let us find out, because in the question we are given that Q1 is greater than Q2. Therefore we can say that charge on the capacitor let us call this as Q cap, will be equal to Q1 minus Q2 upon 2, because we are given that Q1 is greater than Q2. Now we can easily find out the potential difference. You can say potential difference across the capacitor, that is over V will be equal to over Q cap divided by C, that is the capacitance of the parallel plate capacitor. Therefore we can say our V will be equal to Q1 minus Q2 divided by 2C. So this is our potential difference between the two plates. So we get this as Q1 minus Q2 and divided by 2C. Option D is the correct one. Option D is correct. We can also solve this by using the electric field concept, and the electric field between the plates will be electric field because of Q1 plus electric field because of Q2. Okay. That is algebraic sum, which will obviously the electric field be in opposite direction. So we can say E1 minus E2, and we can just substitute value of E1 and E2. We are going to get the same result. Next question. It was asked in the year 1999, and it states that for the circuit shown, which of the following statement is true. So we are given three switches, S1, S2 and S3, and based on this various combination we are given these four options, and we are going to find out which one of the option is the correct one. Okay. And we have to remember that for the capacitor to charge or discharge, the circuit has to be complete. Okay. For example, so if we have a parallel plate capacitor and there is a switch, something like this, and if this switch is open, then there will be no change in the capacitor. Okay. It means it is not going to discharge, even though we require some kind of resistance to be in series, that is going to help us. But in general we can say for the capacitor to behave as a charging or discharging, the circuit has to be completed. Okay. This is the basic behind the capacitor function. It is being to charge if we have some kind of supply voltage connected. So if it is some kind of supply, then it is going to charge. If there is no supply, simple switch, then it is going to discharge. And if it's having some kind of initial voltage, for example, if this some kind of initial voltage on the capacitor, let us suppose that is V, having a charge Q, capacitance C, it is going to discharge only when the circuit is complete, that is switch is closed. Okay, this we have to remember. So in the first case, when switch S1 is closed, so it means when this switch S1 is closed alone, the positive end is no doubt is connected to ground, but the negative end is still open. So circuit is not complete, so the voltage across the C1 capacitor, which is 30 volt, is not going to change. Obviously V2 is isolated itself, so there will be no change. So option A is incorrect. Okay. And next is when S3 is closed, it says that V1 is equal to V2 is equal to 25 volt. Okay. In this case, we can just discuss this specifically. So it says that when S3 is closed, we have two capacitors, and this is a switch S3, and these two capacitors are connected in series. So this is our V1 having our 30 volt, capacitance is given to us at 2 picofarad, and we have our V2 which is our 20 volt, and this is our C2 which is given as 3 picofarad. And so this was a S3. So in this case, we can just justify the answer based on the previous, that the circuit should be complete. But in this case, there is a little bit, you can say, a doubt also arises, because this means that if we have two isolated spheres which are charged and then they are brought contact with each other, so obviously some kind of charge transfer is going to take place between the two. This is bound to happen even if they are isolated with the other environment, which is specifically the case here also. So if we look, we can see that our V1 is our 30 volt and V2 is our 20 volt. Okay. So there is a potential difference between the two of 10 volt. So ideally we think that there might be some charge transfer from, let us call this as, this is our C1 and C2. Okay. But if we find out the charge on the respective capacitors, that is our Q1 will be coming equal to as 60 picofarad, and our Q2 will be also coming as 60 picofarad. Okay. Send both these charges, that Q1 is equal to Q2. Okay. So both the capacitors C1 and C2 are having the same charge. So it is same situation, which means we have two spheres, and these two spheres are charged independently and then they are connected. So it means in this case the voltage across C1 and C2 will be same. So we get our V1 will be once again our 30 volt and V2 will be also our 20 volt. So therefore option B cannot be correct one, but option D is correct one, that V1 is 30 and V2 is our 20. Okay. You can say option D is correct. And option C, S1 and S2 are closed. So if we close S1 and we also close our S2, still the circuit is not complete because our S3 is open. Okay, so if this is open, so there will be no V1 and V2 cannot be equal to 0. So only possibility is that the correct is our option D is the correct one. Next question. It was asked in the year 1999, and it states that An elliptical cavity is carved within the perfect conductor. A positive charge Q is placed at the center of the cavity. The points A and B on the cavity surface is as shown in the figure. Then, so we have to find out what will be the electric field, charge density, potential and total electric flux. So basic figure is given to us, and we have to keep in mind that the shape of the cavity is elliptical. Okay, so it means the distance of A and B is from the center, that is charge Q, will be different, okay, because of the elliptical shape. So this is our elliptical and charge Q is here, and we have point A is given somewhere here and point B is given somewhere here. So the distance from A and B from the center of this charge is entirely different. So first option is electric field A in the cavity is equal to electric field at B in the cavity. Obviously this is not correct because of the asymmetric nature of this cavity. If the cavity would have been a spherical one, then this option would have been also the correct one. And we come to the option B, and it states that the charge density at A is equal to charge density at B. So obviously because of once again the asymmetric nature of this elliptical cavity, this charge density cannot be same. Once again, if it would have been a circular cavity, this option would have been the correct one. And we come to our option C, and option C states the potential at A is equal to potential at B. Okay. And we know that it is a perfect conductor. Okay, because of this perfect conductor, the entire surface is act as a equipotential surface. So we can say that entire surface of a conductor acts as a equipotential surface. Equipotential. Therefore, we can say that potential at A will be equal to potential at B. So option C is correct. C is correct. Now we come to the last option, and it says that total electric flux through the cavity is Q upon epsilon naught. And this is directly, you can say, using the Gauss law. If we consider a Gauss surface which is something like this, and that our flux will be equal to Q upon epsilon naught. So you can say that our, according to Gauss law, flux enclosed surface is Q upon epsilon naught. This is flux of enclosed surface that is only dependent on the charge, not on the shape. So option D is also correct one. D is correct. So here this shape of elliptical orbit, elliptic conductor cavity rather, plays very important part. If it would have been the circular shape, then all the options A, B, C and D would have been the correct one. Next question. It states that three charges Q plus Q and plus Q are placed at the vertices of a right angled triangle, that is isosceles triangle, as shown. The net electrostatic energy of this configuration is 0 if Q is equal to 0, Q equal to, we are given, let us suppose this is triangle A, B and C, which is isosceles triangle, and it is given that net electrostatic energy is of the entire configuration of entire system is equal to 0. So it means this our U of the system is equal to 0. So from here we can write the energy of individual charges will be equal to Q upon A plus capital Q small q upon this will be also A, because this is isosceles, and we can write this as A square, and this comes as square root of 2 times A. So this comes as 2A plus this will be also our Q capital Q divided by A should be equal to 0. Therefore we can easily solve it, and we can take A as common, or Q K upon A will be coming as common. So we are left with only Q plus capital Q divided by 2 plus capital Q is equal to 0. So this gives us that Q we can take, let us take LCM, and this comes as Q, this is 1 plus square root of 2 divided by square root of 2 is equal to minus of Q, and this gives us that our capital Q will be equal to minus of square root of 2Q divided by 1 plus square root of 2, and divide and multiply by square root of 2. We get this as minus of 2Q divided by, this will be coming as 2 plus square root of 2. So we get minus 2Q. Option number B is the correct one. Option B is correct. Next question. It was asked in the year 2000, and it states that a parallel plate capacitor of area A, plate separation D and capacitance C is filled with 3 dielectric materials having dielectric constant K1, K2, K3 as shown. If a single dielectric material is to be used to have the same capacitance C in this capacitor, then the dielectric constant K is given by, and basic figure we are given. We have 3 dielectric constant K1 and K2 and K3, and this K1 and K2 are placed such that the area is divided in half, and K3 is placed such that the area is our A, but its width is our D by 2. So this will be our D by 2. So we can just draw its equivalent circuit, and this equivalent circuit will be our this K1, K3, let us suppose is represented as our C3. So this will be C3, and K1 and K2 will be coming in parallel. So this is our K1 giving a capacitance C1, and this is our K2 giving a capacitance of C2, and like this. So from here we can see that our C1, which is a result of K1, and this is our K2, and this is respectively for our K3. Therefore we can write that our C1 will be equal to, we have this as K1, and epsilon naught area is our A by 2, not D, A by 2, and the width is, the distance is also our D by 2. So this comes as K1 epsilon naught A upon D. Similarly, we can find out our C2. C2 will be also equal to our K2 epsilon naught A by 2 and D by 2, which gives us K2 epsilon naught A divided by D. And finally, we can find out our C3. C3 will be our K3 epsilon naught area is our A, but the width is our D by 2. So this comes as 2 K3 epsilon naught A divided by D. And we can easily find out the equivalent capacitance of this entire system. And you can say our C equivalent will be equal to the C1 and C2 will be in series, in parallel. So this equivalent we can write it as, so this will be our C1 plus C2 and this will go C3. So C equivalent, obviously this entire is in series, so we can write 1 upon C equivalent is equal to 1 upon C1 plus C2 plus 1 upon C3. And we can just substitute the values and we get this as 1 upon C1 and C2. C1 and C2 are almost same with a minor difference of K1 and K2. So we can just write it as epsilon naught A upon D, and this comes as K1 plus K2 plus, and this comes as 1 upon C3 is our 2 K3 epsilon naught A upon D. And we can take epsilon naught A this as common, so we get this as D upon epsilon naught A, and it comes 1 upon K1 plus K2 plus 1 upon 2 times K3. And if we can say our C equivalent, it says that having a dielectric constant of K. So we can say from here that our C equivalent will be equal to K epsilon naught A upon D. So we substitute it, we get this as 1 upon K epsilon naught A upon D is equal to, this comes as D epsilon naught A, and it will be equal to our 1 upon K1 plus K2 and 2 times K3. And from the looks of it, we can clearly see that epsilon naught A and D cancels out. So we get 1 upon K will be equal to 1 upon K1 plus K2 plus 1 upon 2 times K3. So we get option number B is the correct one. Option B is correct. So in this type of questions where we have a capacitor which is subdivided with respect to the dielectric, always try to find out the equivalent basic structure of the capacitors with respect to their respective dielectrics, like we did here, K1, K2 as well as K3, then sort it out. It will be much more convenient. Next question. It was asked in the year 2000 and it states that 4 point charges plus 8 minus 1 plus 8 are fixed at points minus plus and minus symmetric respectively on the y-axis. A particle of mass 6 into 10 to the minus 4 kg and charge 0.1 microcoulomb moves along x direction. Its speed at x is equal to infinity plus infinity is v0. Find the least value of v0 for which the particle will cross the origin. Find also the kinetic energy of the particle at the origin. Assume that the space is gravity free and 1 upon 4 pi epsilon naught is given to us 9 into 10 to the power 9. So we are given that we have the charges and these charges are placed on the y-axis. So we can just draw an approximate diagram. So this is our x-axis and this is our y-axis, and the placement is symmetric. Okay. Therefore we can say that, let us suppose this is our A, this point is our B, and this is our positive. So this is our square root of 3 by 2 plus, and this will be plus square root of 27 divided by 2. Similarly on the negative side, let us suppose this is a C and this is our D. So here we get minus square root of 3 by 2, and here we get minus square root of 27 divided by 2. And the value of charges are also same. There is some, okay, here it has to be plus, other are negative. So we get, one second, this is our A and this is our B, this is our C and this is our D. So yes, so there is some, let me correct the signs. So A, this will be positive and this will be negative. So at D, let us suppose we have a, no, it's correct, it is a positive, my mistake, and this is also negative. So we get at A, we are going to suppose minus of Q, and this is our plus capital Q. Similarly this will be minus Q and this will be plus capital Q. Yeah, now it's correct. And we are given a charge that is our 0.1 microcoulomb and it is coming from some kind of infinity point. Okay, so let us say this is our having mass m and this is our q naught. It is moving towards the origin with the velocity v naught. At some instant, let us suppose it is at point P, and the distance of this point P from the origin is our x. So because of symmetricity, let us join these points. So we can say our AP will be equal to PC. So we can say our AP will be equal to our PC, and this distance is our root 3 by 2. So we can say AP by PC will be equal to root 3 by 2 square. So this comes as 3 by 2 plus x square and its square root. Similarly, our BP and our DP will be also equal. So we can say that our BP is equal to DP, and here it is square root of 27 by 2, so which comes as 27 by 2 plus x square and its square root. So now we can easily find out the electric potential at point P. Electric potential at P. Obviously it will be the summation of potential due to individual points, individual charges. So we have plus Q, so potential will be, because of these two will be adding, that is a plus 2 something. Similarly, this is minus Q and minus Q, so in this case it will be minus of twice. Okay. And let us call this as potential at Vp. Therefore we can write our Vp will be equal to our K, and the charges are 2Q divided by our distance, that is Bp, and this comes as K. Once again, this is our 2Q and Q is our AP, and K we already know is our 1 upon 4 pi epsilon naught, whose value is given as 9 into 10 to the power 9. Therefore we can substitute the values and we get that our potential K we can take as common, 2 also as common, and we get this as 2 into 9 into 10 to the power 9, and capital charge Q is given as 8, and Bp is our 27 by 2 plus x square and its square root minus, and we have this as other charge is given as 1 microcoulomb. Okay, and this will be our 1 divided by 3 by 2 plus x square and its square root and 10 to the power minus 6 because of the microcoulomb. And we need to find out the electric field, which will be the derivative of our potential. So we can say that our electric field at P, that is our EP, is equal to minus dV by x. So we get our electric field at point P is equal to, this will become as 18 into 10 to the power 9, and this comes as our 8, and its derivative will be equal to 1 by 2 minus, so this comes as divided by 27 by 2 plus x square and its square root multiply by 2x, and it will be multiplied by minus 1 by 2 because of the power. And similarly for the other side also this will be minus, so we have here 1 upon 3 by 2 plus x square, and this comes as 2x, and this will be minus 1 by 2. And it states that so we have to find out the least value of the, you can say, okay, and we can just sort it out and find out the value of x. So we get this as one second, this will be our 3 by 2, my mistake, minus 1 by 2, and this will be our 3 by 2, and similarly here also 3 by 2, because it will be minus 1 by 2 and minus 1. So we can say that putting equal to 0, we will get this as x will be equal to plus minus square root of 5/2. And we got the value of x, and taking for the positive value, and we see that least value of kinetic energy, that should be enough such that particle, okay, so least value of kinetic energy. So you can say least value of kinetic energy such that the charge particle reaches x is equal to plus square root of 5/2 and at this point we already know that because at x is equal to plus square root 5/2, our electric field is equal to 0. Okay, I forgot to mention that this we have to solve by putting the EP is equal to 0. Then we are going to get this value. So therefore EP is equal to 0, or we can say the force because of this electric field at point P should be equal to 0. So which basically means that if value of x is greater than 5/2, this our electric field is repulsive. Repulsive basically means towards positive x-axis. Positive x-axis, and if x is less than 5/2, this our E is attractive. So which basically means towards negative x-axis. Therefore we can say potential at x is equal to 5/2. So we can just substitute the value as 5/2. We get that our V of P will be equal to 1.8 into 10 to the power 4, and this comes as our 8, 27/2 plus this comes as 5/2 and minus 1 upon 3/2 plus 5/2. So we get our VP is approximately equal to 2.7 into 10 to the power 4 volts. Now we have to find out the energy also. Oh sorry, kinetic energy we need to find out. We only found out the potential. So we can say conservation of energy from x is equal to infinity to x is equal to square root of 5/2. Conservation of energy from x is equal to infinity and x is equal to square root of 5/2. and x equal to infinity, it is only having the kinetic energy, that is half m v naught square. So you can say this will be equal to half m v naught square is equal to q naught multiplied by vp. So from here we get our v naught will be equal to twice q naught multiplied by vp divided by mass m and its square root. Now we simply substitute the values, we are going to get the answer. So v naught will be equal to 2 into charge is given 10 to the power minus 7 into 2.7 into 10 to the power 4, and this comes as 6 into 10 to the power minus 4 square root, which gives us a v naught is equal to 3 meter per second. So this is the value of the velocity that we are supposed to find out. Okay, so this completes all the questions. A total of 9 questions were there, and from 1998 we were having 2 questions, 1999 4 questions, and 2000 we were having 3 questions. So this completes all the 9 questions. Thank you.